All right, so thank you everyone. Thank you everyone for coming to this week's training. My name is Christian Mata. I am the CFD technical specialist for Altair, based out of the West Coast. So I do support and have worked with most of the people that focus on anything CFD related. Usually if you have any questions regarding CFD, you'd probably hear from me. For the most part, anytime that I work with most of the customers that are based out of the West Coast, but I do have some customers throughout the U.S. as well that I've worked closely with. I've been with Altair for about 4 years now, and I'm pretty much kind of like the first level of support for anything CFD related. So if you guys, what I'd like to do is kind of like give you guys an idea as to what we're going to be covering and how this is going to be laid out. For the most part, I'd like to start off by giving you guys the link to download the day's material at the beginning of the session. After that, we'll be covering a few different topics here. So I'll start by kind of showing you guys the agenda here. And we'll be going through a few different topics throughout the days here. For the most part, we'll be covering very basic things today, kind of things like just showing you guys how the interface works and basic controls of the camera. But for the most part, what I'd like to kind of tell you guys is that the training will be, I would like to keep it as interactive as possible. So I do want to welcome you guys to ask any questions, or if anything does come up, I'll be happy to answer any comments that you guys might have. So do feel free. It's not going to just be me showing you guys a bunch of slides and just kind of showing you how to do things. I would like to kind of have a little bit of back and forth between you guys. So I do welcome you guys to ask any questions if anything does come up. If you need me to repeat any step at any point, please feel free to let me know. For the most part, when it comes to the slides, I do prefer to go through the slides fairly briefly and then just show you guys through the demo what exactly I would like to cover for you guys. So that's kind of the idea behind this. So even though it is an online training, that's kind of the main thing that would be a little bit different from, say, just watching a recording. I would like to kind of keep this a little bit more interactive. Now, when it comes to the actual demo, we'll usually go through a few slides and then we'll do a physical demo each day. Once we get through the demo, I'll be going through the different steps. If I see a question that does pop up very often, or like if it comes up a lot from several people, then I might address it right on the spot. Sometimes I also like to take some time at the end of the training to answer any other questions that you guys might have. So to get started here, the first thing that I want to talk about is mainly just some very basic introduction into just the CFD world in general. We won't be going too deep into like the actual theory or anything like that. We're just going to be mostly covering the basic methodologies, the basic concepts behind a lot of this, the basic workflow as well, and just what are some of the main things to consider. So when we're talking about CFD or just any type of fluid analysis in general, there's three main methods that are used to try to figure out, how the fluid is behaving in a particular scenario. There's an analytical approach where we try using things like, equations and different equations that we have in order to try to compute and calculate a general idea as to what we're trying to solve and get like a good estimate as to what would happen. Now, this can be a very difficult method of doing things, but it is sort of, in some cases, it is a good first step to give you an idea as to what kind of numbers you would be expecting. There's also the experimental approach where we physically test and build either a scale model or a full-size model and do things like wind tunnel testing or different types of testing for a physical model. There's obviously some advantages and disadvantages to each one, but that's another method of kind of figuring out how a fluid would behave in any type of application. Then the last method, and that's the method that we're mostly interested in, is the numerical approach, where we use computers and computational models to capture the physics of a fluid moving through a component or a part, and we get a very good estimate, a very good idea as to what is happening within the model. It allows us to work with much more detailed models as compared to, say, the analytical approach, but there is some limitations to that as well. So the first thing that I want to kind of talk about is just, like I briefly just mentioned, this the analytical approach uses things like the Navier-Stokes equations, and you use some boundary conditions to compute and calculate or get an idea as to what the values would be using math and hand calculations to try to get an idea as to what your model is. Now, some of the advantages to this is that it could give you a very good idea at the very beginning, or you get a pretty good estimate. However, it's a very difficult to do and very time-consuming method to do. So it's not typically used to try to do very complex models. So for the most part, it is used for things like getting an idea as to what kind of values you would expect, and that's some of the applications that I've used for using the analytical approach. Now, when we're talking about the experimental approach, this has a lot of advantages in that you're physically testing the model that you're working on, which means that your results would be a lot more reliable than other methods because you're not really making as many assumptions. You're sort of actually testing it. You're physically testing it. So there's a big advantage to using an experimental approach, which is that you have much more reliable solution or answers. You're physically testing the model, so you know that the numbers you're getting are much more reliable. But there are some drawbacks as well, where, as for example, you do have to either build a scale model or a full model, which means that it could be very expensive, and in some cases it could be very difficult to build a model just because things like prototypes can be very expensive. There's just the experiment itself can be very expensive to run as well. For example, just operating a wind tunnel would be a very expensive way of going about any kind of experimental approach. So there are some drawbacks to using an experimental method. And if you're trying to test a part that doesn't exist yet, then you are kind of limited to having to build either a prototype or a scale model of this. Now, the other drawback is that, let's say you want to make a slight adjustment or any small change to your model. In those cases, then you would have to build a new prototype, which would be, again, more expensive, and then do, again, more experiments, which also be very expensive as well. So there are a lot of limitations to the experimental approach, even though you do get some good results out of that. So that's where the numerical approach comes in, right? So the numerical approach is kind of like the best of both worlds, where you can get a very good estimate as to what the solution would look like. You can try various models that in most cases don't even exist yet, and you can try and test different characteristic changes or maybe some feature changes on your model that will let you, make adjustments or test different prototypes very quickly, as opposed to, say, an experimental method. But you can also test much more complex geometry as opposed to, say, the analytical method using equations and whatnot. So there are some advantages to it. The only disadvantages is that you are limited by, and the biggest limitation to the numerical method is that you are limited by computational power. So it's very dependent. The computational power is going to be something that does limit you in many ways. And as we move forward through the training, you'll see that there's going to be a lot of different things that are mostly just limited by the amount of computational power that you have. So in some cases, some very complex models can be a little bit more time consuming. So that's one drawback as well, where setting up a model can take, it could take quite a bit of time depending on how complex it is. And also the solution of the model can also take a lot more time as well. So even though you're using computers to do most of the calculations and the computation for you, you do have to spend some time in refining the models. There's your solution has some limitations as well, and is sensitive to a lot of different parameters as well. So there's some sensitivities that go into any type of CFD analysis. So I will spend some time talking about those as well, but that's just kind of to give you an idea as to what are some of the advantages and disadvantages to a numerical approach as well. So I guess I just briefly talked about the advantages, so we can continue to the next thing here. I do have quite a few slides here, so I want to make sure that I don't spend too much time on the slides here. I did see more people come in, so again, I will post the link to download the material for today's training. It's in the chat box right now, so please take a minute to download that material. So if you go over to the chat box, you will see a link there that allows you to download the material that we're covering right now. Okay, so when we're talking about this, any type of CFD analysis or the general process that we go through when we're trying to do a CFD analysis, in general, there are some basic steps that we take in order to try to get a solution. So for the most part, it always starts off with the preparation of a model. So we'll bring in a model, we'll do some kind of cleanup, or we'll make sure that our geometry is, accurate or set up correctly so that we can start generating the model around that geometry. So that's usually the first step that we'll do. So we'll normally either bring in geometry from another CAD package, and we'll start doing any kind of cleaning inside of that. We also have, in this case, we have some tools that allow us to generate some of the geometry within the software as well. But do keep in mind that this software package is not necessarily like a CAD package, although you do have the ability to create some primitive shapes. It's not ideal for you to generate like an entire model within this software. Ideally, you would normally bring that in from another CAD package. So now we start off with the model preparation. So we'll bring in some geometry. We'll start generating the actual fluid volumes that are in our geometry, and we'll do any kind of cleanup that we need as well. From there, we'll start doing the actual setup of the simulation, where we'll start setting up things like the material properties, what kind of boundary conditions we have on the model, and if there's any kind of things like heat sources in some cases. That's usually the next step that we take when we're setting up any particular model. Now, the next thing after that is we do the mesh setup. So the mesh setup would be where we grab that geometry that we just brought in and we set up, and we sort of split it up into small elements that allow us to do the actual computation itself, right? So the mesh setup and meshing stage, and hopefully a lot of you guys are already familiar with what meshing is and what it entails. But the idea is that we grab our geometry, we split it up into smaller blocks, and we run the computation, or we run the solution of those equations on each one of those blocks. So what that tells us is that we do spend some time making sure that our mesh or these elements are created accurately, and making sure that everything is ideal for the solution that we're trying to do as well. So then after we do our meshing stage, and then let me get my pointer here. So after we do our meshing setup, we do move down to this solver run. So what ends up happening is there is sort of 3 stages through to any type of analysis, and this applies for CFD as well as like structural analysis and other types of simulations. For the most part, we have what we call a pre-processor, and then we have a solver, and we have a post-processor. So these 3 things would require 3 different types of software in some cases. So what that entails is that when we look at these first steps, when we look at the model setup, the simulation setup, the mesh setup, all of this is done in what we call the pre-processor. So this would be all done in one piece of software, in this case being HYPERWORKS CFD. And then once we finish setting up our model, what we end up doing is we send that model to the solver, which is another piece of software. Now, this other piece of software, all it really does is it grabs the model that you generated originally, and then what it'll do is it'll compute a solution for you. So it's kind of like a calculator, I guess you could call it, right? So it's what what grabs your model and starts giving you an actual answer. So now once it does compute everything and it gives you a solution, the next step from there is to do post-processing. And post-processing in some cases will require another piece of software as well. So there's these three stages. We have the pre-processor, the solver, and the post-processor. So just kind of keep that in mind for now, just because I will be throwing in different names to different softwares that we'll be using. So just kind of keep that in mind. There's three different stages: pre-processor, solver, and post-processor. So now, like I mentioned, in the model preparation stage, we'll usually bring in some kind of geometry from another CAD package. And once we bring in that model, sometimes depending on the way that the format gets exported, sometimes there can be some need for cleaning up the geometry. So one thing that sometimes happens, and this isn't something that's just like exclusive to our software, it's just something that happens when you export models. There can be some, I guess you could call them errors in the geometry. Let's say when you grab something from one CAD package that's saved in a certain format, and then when you convert that to another format, something like Parasolid, IGES format, or STEP format, there could be some errors within that, which will cause some geometry, I guess you could call them like bugs that happen, where the geometry will have little imperfections that will be created just out of like an error, mostly, not necessarily. You don't see it too often. It's not something you'll see all the time. It's something that tends to happen every once in a while. But when it does happen, we do have some tools that allow you to clean up the geometry, make changes to the geometry, make adjustments to the geometry. But all of that would be done in this, what we call the model preparation stage. So now once we do generate this geometry and we have everything that we need, for example, another thing that we can do is we need to create the actual fluid as well that we're going to simulate. So for example, if you bring a pipe, you need to have the volume inside of that pipe, the actual fluid that goes inside of that pipe, right? So if you bring in a hollow pipe, we need to fill it in with material with another piece of geometry that will be covering pretty much what the fluid would be inside of a pipe. And a lot of this will make a little bit more sense once we start going through the different models. But the idea is that since we're going to do a fluid simulation, we need the geometry of the fluid, not so much the geometry of the actual solid part, right? So depending on the kind of analysis you're doing, in some cases you might need to generate just the fluid, right? So the fluid is the main thing that we care about. So that's all the stuff that goes into this model preparation stage. After that, what we'll end up doing is we'll go into this simulation setup stage. And this is where we start setting up things like our boundary conditions, what kind of inlet velocities we're going to see, what kind of pressures, temperatures, things that we would want to define in our model. All of that gets done here. Also things like whether our model has radiation, whether there's what kind of turbulence model we want to use. There's a lot of different things that go into this simulation setup stage. And from here, normally what we'll do is we'll start making some assumptions. We'll start defining things like we'll define things like walls, any kind of heat sources. All of that gets defined in this simulation stage. Now, once we're done with that simulation stage, we jump into that meshing stage. And what ends up happening here is we grab that model that we've been working on and we set up, and we start splitting it into these smaller sizes, these volume sizes, or either squares or triangles, or cubes or tet elements. We call those elements, and those are the ones that we want to split our geometry into. Now, when we generate these meshes, what ends up happening is we grab this model, we look at our geometry, we look at our mesh, we make sure that our mesh is capturing the geometry accurately, and we make sure that our elements themselves aren't warped too badly, for example, or making sure that we have enough elements to capture any kind of special physics around the model. So we will do any kind of reviews and fixes, and anything regarding the meshing we'll do in this meshing stage. Now, to kind of briefly go into what meshing entails, we do split up our geometry. For example, here we have this sort of pipe that has a fluid inside. So you'll see I have elements on both the pipe and the fluid inside. And what we'll do is we'll usually split up the geometry into these small either triangles or squares, and we'll generate these elements, right? So some of the supported elements that we do have for this solver are, we support hexahedral elements and tetrahedral elements. So the idea here is we'll grab the geometry, we'll split it up into different elements, and I'll talk into some of the sensitivities that go into the meshing as well, where let's say if there's any kind of mixing, very active mixing that's happening within the fluid, then we'll want to refine our mesh. We'll want to have the smallest elements possible. So the idea with meshing is that the smaller the element size is, the more accurate your solution will be. The thing is that the smaller those elements are, you have a larger amount of elements, which means that your computational time will go up. Okay, so that's one of the cases where computational power is a limitation. So technically you can generate some very, very, very small elements, but always keep in mind that the biggest limitation is going to be the computational time, or how much computational power you really have. So once we're done with that, what we'll end up doing is we'll grab that model, we'll grab that mesh, we'll export it into the solver. In this case, the solver program that we're using is AccuSolve. So our pre-processing software is HYPERWORKS CFD, and then that gets exported, that exports our model to the actual solver, the actual thing that's giving us a solution, which is AccuSolve. So AccuSolve is our solver software. Okay, so this gets sent out into another piece of software. So just kind of keep that in mind. Monitoring solutions, then we'll be looking at our solution. We'll be kind of making sure that our solution converges. And what I mean by convergence is just making sure that our solution is making sense in a way. It's just mostly making sure that our solution is being solved correctly. So that's the idea with this solver stage. And then once we're done solving the problem, then we go into post-processing, where we actually look at our solution, we look at our model, and we look at what needs to be, or what happened to the actual problem that we set up, right? That's where we see the actual answer in the post-processing stage. Now we have some CFD applications. Now, before I jump to the next thing, do you guys have any questions so far regarding anything of that I just covered, any of the meshing stages, the solution, the problem setup? Anything you guys might have any questions on? Okay, well, the questions start coming in. What I'll do is I'll show you guys just briefly what are some of the different applications that we can use CFD for. We have tons of different uses for this, where we can, for example, simulate the mixing of different fluids, or the actual flow of a fluid inside any kind of component. We can see a model here where we're filling a tank. That's another application where we use, for example, things like multi-phase flow, where we'll have two different types of fluids. We have technically like air inside and water coming in. We also have thermal applications, where we'll see how this is kind of like a flame, it looks like, and we see how the heat is being transferred through the fluid domain that we have in here. There's a lot of automotive uses as well for this, where we can see the aerodynamics and external flow applications. So external flow applications are really useful as well. There's also internal flow applications, where we can combine things like thermal and flow. So the actual heat changes for a pipe, and we can also see the different types of pressures that affect a model, and we can we can use structural models and couple structural models to combine the two in order to be able to see what the physical deformation of the part would be based off of pressures and the flow or temperature changes in a model. So there's a lot of different applications for CFD, but there's a lot of different uses for it. So you guys can kind of think of what applications or what kind of methods you would use for your particular applications. So, now before I go to this next section, do we have any other questions, anything at all? All right, so, okay, so when we're talking about sensitivities, what I really want to just kind of discuss is what are some of the things that affect your answer? So that's kind of like the short version of that. So when you bring in a model, there's a lot of little things to consider that can have a big effect on your actual answer. So when we get any kind of CFD result, you got to kind of keep in mind that there's a lot of little things that will affect the actual solution. Things like your meshing, the actual physical models, and I'll go into what each one does. But there could also be maybe different types of errors that maybe either we commit or an error that happens within the solution. So there's different things that can cause problems within our model, and there's just a few things that we would want to look out for. So for example, we have modeling errors where, let's say we bring in a model, but we don't quite specify the boundary conditions correctly. That could cause different types of errors in our model once we try to solve it. There's iteration errors, discretization errors, where it's just mostly based on how well you define or how well you capture the actual geometry itself, or how well you capture the actual physical aspects to the model itself. We have rounding off errors where maybe we make some assumptions, or maybe there's just like different numbers that get rounded off throughout our actual solution that will cause different types of errors as well. Input errors where we just literally just put in the wrong number. And in some cases, there could be also code errors where we run into some kind of bug in the solver, or some kind of issue where the solver doesn't like a particular setup for your model. But the main thing to consider when it comes to all these errors and all these sensitivities is that when you set up a model, your solution's really only going to be as good as your assumptions are. So what you'll see is that once we start working through one of these models and we start setting up different aspects to it, one thing that will happen is we'll start setting up a model, and we'll make some assumptions, and if our assumptions aren't very good, or if we just make some very broad assumptions, our result, the solver will give you an answer, but it might not be, accurate, or it might not be right, just because based off of the information you gave the solver, there could be some issues with that as well. So just kind of keep in mind that your answer is only as good as your assumptions are. So when we start setting up these models, it's always good to try to base everything as much as we can on either test data, or other types of experiments that we've done in the past, or things that are well known, but just inputting random numbers can give you a very random solution, in other words, right? So just kind of keep that in mind. We want to get as good of an answer as we can, and sometimes it's kind of up to us to make sure and distinguish whether our answer is good or not, or if it's accurate enough or not. So that's kind of the idea when it comes to thinking about what are some of the assumptions that we want to make in our models. And as I start setting up these models, I'll discuss how we can make assumptions, what are some of the smarter ways to make assumptions, and so on and so forth. So when we look at these sensitivity studies, there's a lot of things that our model is sensitive to. So for example, when we do things like generating a mesh or making changes to our model might react differently to different quality meshes, for example, or different ways that you might set up the boundary conditions, or different turbulence models you choose to use. But for the most part, the idea is that we want to make sure that our accuracy is good, and we have our model give us a very accurate solution based off of the model that we set up. And we want to make sure that there's not as many outside effects like making our model misbehave or give us different answers than what we're really looking for. So there's different methods of performing these sensitivity studies. And what I mean by a sensitivity study is that you want to kind of grab, let's say you want to look at the way that your mesh affects your solution. Because like I mentioned before, the finer that mesh is, the smaller those elements are, the more accurate it is. Now, there's a certain point where your solution's not really affected by the size anymore, just because your element size is small enough to capture whatever's going on in that area accurately. So making it smaller would probably not make a difference. However, on the other side of that, if your mesh is too coarse, your element sizes are too big, one thing that could happen is that your solution might be erratic, or it could behave very weird, and your solution might not make much sense. So in order to make sure that our model is not misbehaving due to something like a mesh or some kind of parameter that you can adjust, we would do what we call a sensitivity study, where we try different sizes, for example, or we try different methods one at a time to make sure that those certain parameters are not affecting our solution. So the idea is that when you do any type of sensitivity study, you want to evaluate one aspect at a time. You don't want to change too many things on your model at once and then try to run it. It's usually ideal to just look at one aspect of your model, test different settings for that, and then if you get a better answer, then that would be kind of the idea behind a sensitivity study. Now, there's different types of sensitivities. One thing is geometric sensitivity, and what I mean by geometric sensitivity, that's just basically just simply how good your geometry is, right? So making sure that the geometry, in some cases, the actual fluid is created correctly. There's nothing that could cause meshing errors or meshing problems. So one thing that you'll notice is that once we start bringing in these models, you'll have these edges around your model that the mesher uses as kind of a reference to generate these elements. So for example, these elements that we have here, they will try to fit and match certain geometry or aspects of your geometry correctly. But for example here, these fillet areas, since we have two edges, we probably have one edge there and one edge there. The mesher will try to fit elements where these lines are. And sometimes those lines just don't make sense and we don't need to have those lines. So that's where we look at our geometry. We try to clean up our geometry as much as we can. And that's where we would consider that to be a geometric sensitivity. So also another thing about your geometric sensitivity in cases like your external flow applications, like let's say you're doing some kind of external flow, the actual size of that, let's say that wind tunnel, also affects the answer as well. So your model is also kind of sensitive to the size of the wind tunnel that you would be creating if you're doing some kind of external flow application. So kind of keep those things in mind, that your geometry is kind of sensitive to a lot of these things. So if we bring the walls in close to our model, those walls could probably have an effect on the flow of our part if we bring them too close to our actual geometry, for example. Then there's also mesh sensitivities. Mesh sensitivities, I was just talking about this. So the mesh sensitivity mostly focuses on how fine the mesh is. So the idea behind it being that you want to create these elements as small as possible, right, within reason, so that they can capture the geometry, capture the physics, capture the flow correctly. So because in some cases you might have, let's say, a small pipe that connects to a larger area, and that flow that's coming from a smaller pipe might mix with that larger volume. So you want to make sure you have a small enough size coming in, or a small enough element size in that area where you would have any kind of mixing. But for example, out in the corner where nothing's really happening, you wouldn't really need a very fine mesh. So what the mesh sensitivity, or what we want to consider when we're creating these meshes, is mostly making sure that our element size is small enough to capture anything important that's happening in our model. Okay, so that's the basic way of putting it. But do keep in mind that we don't want to just make it super small all the time, because what will happen is that we'll increase our computational time quite a bit. And one thing that you'll see is that if you do any kind of mesh sensitivity study, you'll see that you do get sort of diminished returns as you make the mesh size smaller. So one thing that will happen is that at the beginning you'll have a very large mesh size on this, so your mesh will be very coarse. And the finer you make it, the solution will get a little bit more accurate, right? It'll be a little more exact. The thing is that you start getting it to a point where, let's say you cut the size in half, you make the size like half the size, and you'll get very slight improvement. And then you'll make it half the size again, and you'll get an even smaller improvement. So there is sort of a limitation. There's a sort of a diminishing return. So that's where we need to kind of make this decision as to how small do we really need to go? How detailed do we have to be for certain things? And is there an importance to making a small mesh size in certain areas where nothing is going on, for example? So it's important to kind of keep this in mind. You don't want to make your mesh tiny all the time, because number one, it will make your computational time very, very long. So you could be, hours and hours and hours trying to solve something that you could have probably solved with 30 minutes, and maybe you only see, a 1 or 2% improvement or something like that. So that's one thing to kind of be wary of and be careful with. Don't always make it super small. So the idea is that we want to make the mesh as coarse as we can without sacrificing accuracy. So that's what we want to look out for when we're trying to do any kind of mesh refinement. Now, when we're looking at the mesh refinement, those are pretty much the main things that I was just looking for. Another thing that's kind of important when we're looking at meshes is things like element skewness. So one thing you'll see is that as the mesher tries to fit these elements in your geometry, sometimes it'll warp some of these elements to make it fit in your geometry. And there's a certain level of skewness that's acceptable, but you do want to be careful with it, not like, say, being too collapsed and giving you issues later on. AccuSolve is really good at handling these type of skewed elements, but there are some limitations to that. Like, you don't want, your aspect ratio would be another category for that as well, where you would have to kind of be careful to make sure your elements aren't too big or too small, or like transition from very small to very big too quickly. You also want to watch out for those growth factors as well. So you want to make sure that you're going from these smaller elements to those larger elements in a very smooth and a nice transition. You don't want to jump from tiny elements to huge elements very quickly either, because those things will affect your solution as well. So there's a lot of little things to watch out for. And as we start setting up this model, you'll see some of these parameters that allow us to control this. So I want to kind of skip through some of these. I don't want to spend much more time on slides. I don't want to bore you guys to death with slides here. So boundary condition sensitivities, that's another thing. You'll see that there's different ways of defining your model, different ways of defining what your inlet and outlet conditions are, the way that your heat is being transferred in your model, or how it's being generated in your model. All of those things are things to watch out for, and these are pretty easy. You just kind of have to visualize the model, how it behaves in the real world, and you want to try to capture those boundary conditions as much, or make them as accurate to the real thing as you can in your CFD model. So I'll skip through some of these slides here. Now, one thing to consider when we're talking about boundary conditions, for example, the way that your model can be sensitive to something like a boundary condition, if we're looking at the way that this, for example, this flow going through this pipe here, going over this step, you'll see that we have some kind of wake that's happening down here. So you'll have some slower flow moving down in the bottom here. The flow comes in, but let's say we consider different places to put our outlet condition, right? So our outlet boundary condition, if we were to put it where this white line is right here, we could be cutting off where the solution is. So like, let's say we started running the simulation It'll give us an answer, everything will be fine, but we won't be capturing everything that's going on. We'll be missing out on the rest of the flow that's happening over here. So we'd be cutting it off a little bit too early if we put our outlet boundary condition too early on here. Now, if we move it further down the line here, you'll see that now we'll be able to capture all of that little blue area where the stagnant flow is, but then we might be capturing that, but we don't give it enough room to kind of finish creating that profile that we need towards the end here. So we're still cutting it off a little bit early. So if we were to put it down here, you'll see that right here, the profile has kind of already been generated. It's kind of stable there. So there's nothing else really happening towards the back here. So any point from here on, you would be fine setting your outlet boundary condition right there. So if you were to put it further back this way, you'll see that you'll still get the same answer, but now you have all these extra elements that would be in the middle here. So there's a lot of little things to consider like that. We want to make sure that we're not cutting off the flow ahead of time. We want to make sure that we're giving it enough room to kind of like breathe and to be able to produce these profiles and finish generating the flow that it wants to do. So we want to give it a little bit of space, and we want to make sure that we don't cut it off early. But we also don't want to make it too big to where we're not really benefiting from that. So that's what we would consider what we call a boundary condition sensitivity. Now, I believe this is the last category here, the physical model sensitivity. This is just how we define the actual physics themselves. So for example, if we have some kind of, one example that I can think of right off the top of my head here, if we have some kind of thermal model where we have some kind of heat transfer, we can use these heat transfer equations that we normally turn on, but what about radiation? Whether you choose to use radiation or not could have a big effect on your model, right? So your model could be sensitive to some of these equations. Or another example would be turbulence equations. So as I'll discuss in one of the future classes when we talk about turbulence, once we start talking about turbulence, there's different turbulent models that we can use, and some are a little bit more detailed than others. But then depending on whether we use turbulence or not in our model could affect our solution as well. So that's how our model is sensitive to the physical parameters that we specify in our geometry here. So yeah, that's the example of the turbulence that I was just talking about. We do have a ton of different turbulence models that we can use. So depending on which one you choose, you could have a good solution or a bad solution as well. Just your model might be more sensitive with one turbulence model or another. So that's just some of the ideas. Material properties as well. Let's say you don't define your material properties accurately. Your model could be sensitive to that as well, and that could affect the results. Heat transfer I just mentioned, and I believe that's pretty much it here. I know I mentioned briefly convergence. So when we're talking about convergence, we're kind of looking at how well our solution is coming out, I guess is a simple way to put it. We want to have convergence in our solution just to make sure that each one of the time steps or each one of the iterations that your solver is doing at least coincides or at least is making sense as you progress through the solution here. If you were to, and I'll show you how to look at these plots, but if you were to look at your plot and instead of having convergence, you have all sorts of jumping around in your model, that could mean that your solution is not quite giving you a reliable answer, and it's probably something that you would want to be wary of as well. So that's another thing to consider when we're talking about the sensitivity of convergence. We're looking at things like, for example, if you're doing a steady state run, maybe not giving it enough iterations to converge, right? So maybe the solution will start converging and it'll start dropping. This value will start dropping, and the lower this value goes, usually the better your solution will be, which means that if you cut it off a little bit too early, then your solution might not be as accurate as you would expect. And the idea of convergence sensitivity is that you want to give it enough iterations to converge, but without going overboard and having to wait so much time. Like, for example, if you're doing a transient solution, In those cases, then we'd look at things like staggered iterations, and I'll discuss all of this stuff once we start setting up these models. But the idea is you want to give the solver enough iterations to be able to give you a good solution. So now we can start actually looking at the software here. So while I start setting this up, I'm hoping that you guys got a chance to download the material by now. And also I can take a few minutes here to answer any questions on the million slides that I just showed you guys. Anything that you guys might have a doubt on, anything you guys aren't too sure about, please take a minute to, I'll take a minute to answer any questions while I start opening the software here. So what we want to do here first is make sure that we have the software installed, and what we want to open is HYPERWORKS CFD. So I'll start by opening HYPERWORKS CFD, and I'll get that up and running. And I'll take this time to take any questions. All right, I don't see too many questions coming in, well, any questions coming in, so I guess I'm a very good instructor here, but let's get started here with the actual demo. So what we want to do is we want to start off by first importing or opening up the model that I just sent you guys. So the model that I sent you guys in that zip folder that you guys should have downloaded by now. What we want to do is we want to go into File and open Geometry. I believe it's a piece of geometry. And we want to do the manifold, so manifold parasolid file, and we'll click Open. You'll see this window pop up. For now, let's just click Open. I'll break down a lot of this stuff as we go along. I don't want to throw too much stuff at you guys at once. But here we have this manifold. Now, were you guys able to open this without any issues? Okay. All right, so getting started here, one thing that I kind of want to break down for you guys is when we bring in a model, you'll see that we have all these icons on the top, and for you guys, you might not see this window on the left here. So by default, I believe you can't see what this part browser here. Just to kind of keep the interface a little bit simplified, if you want to see this window here, all you have to do is you go on top where it says View, and just be sure to check both the part browser and the setup browser here. And those two should bring up the little window that I have on the left there. Now, what I want to start off by doing is showing you guys the basic camera controls. So what you'll see is that when we bring in a model, if I were to click the mouse wheel, that allows me to rotate my part about a specific pivot point in the middle there. So if I rotate my model, I can just click the mouse wheel, and while I hold that, I can rotate my model around. If I wanted to pan this model, I can right-click and drag, and you'll see that I can move my model around. So these controls are a little bit different, especially for you guys that are used to HYPERWORKS Classic. So for the most part, these are the two main controls that you'll be using. Now, let's say you want to rotate your model about a particular point, so some specific point around your model. Let's say you zoom into this area here, and you want to rotate your model around that point. If you click on your part once using the mouse wheel, if you use the mouse wheel and just click once, you'll see that it'll change the pivot point on there. Wherever you click on there, it's going to be the new pivot point for your part. So that allows you to zoom into a geometry and just rotate your model about a specific point. Okay, so this is the volume of air that goes inside of a manifold. Ideally, for any kind of flow application, you just need the actual volume of air that goes inside of your part or around your part. Unless you're doing any kind of heat transfer, most of the time you don't need the actual geometry itself. All you really need is just the actual volume of the fluid that you're working with. So this would technically be the part that goes inside of some kind of pipe or some kind of manifold around this part. So this is ideally what we're going to work on getting in the future classes. But for now, I just want to show you some of the basic controls here. So now, if we look at the bottom here, we have some other buttons that allow us to change our view. So if we rotate this model around, we can change the visualization of our geometry. So we have, if we click this first one, we can save different views. If we click this second option, we have the ability to look at the transparency of our model. So for example, we can do a shaded geometry that makes it transparent and we can see inside of our part. Or we can see just the wireframe of our part. And we can also see the fixed points around each one of the lines that we see on here. So the ones that I most commonly use are usually just the shaded geometry, or if I have a part inside of this, I'll use the transparent geometry. But that's the way that we can change the different shading for this. After that, we have mesh visualization. We don't have a mesh just yet. From here, we have different types of views, and I'll break these down once we start doing a little bit more work. But for now, we have this model orientation here, so we can change the view from top, bottom, left, right, and we have an ISO view as well. On the far right, this one just fits our model to the window size, I believe. So that's what it'll do. There's also different shortcuts for all of these views. So for example, if you hover over that, you see that says fit select and it says the letter F. So if you want to fit your model onto screen, you can click or you can press the F key on your keyboard and that will fit to screen as well as if you click on that also. We also have a section cut tool here that if we click that, you'll be able to create a list of section cuts in your model. So if I click the little plus sign here, you'll see that it cuts my model in half, and this is just hollow right now. There's no elements, there's nothing inside of it right now, but it is a solid geometry. So I can choose to view or hide anything within the section cuts that I create. The next thing that I want to talk about is the layout of the different icons that we have up here. So I'll close this real quick here. If we look at the way that these buttons are laid out, one thing that you'll notice is that everything is set up in a way where the workflow is defined from left to right. So in most of these cases, you'll kind of work your way from the left to the right when you work with most of these tools. So I'll mention that a few times as I go through the actual examples. But one thing that's very special for this type of interface is that we do have within each one of these icons, some of these icons will tend to have different tools within one icon. So if I go in here, you'll see that I have this tool that has two different options. I have a push-pull tool and I have this spin and rotate tool right in the same icon. So it is kind of important to notice that some of these tools will have different options. So for example, under this stitch tool right here towards the top here, you'll see that as I hover over, there's one for stitching surfaces together, and there's one for suppressing edges right next to that. So those are two different tools that we can use within that one icon. If I go to the very first icon, you'll see that I have the new, the folder, and the save icons all within this one icon here. So kind of keep that in mind as you hover over. You'll have different options to different tools as you work through this. And this is just kind of to give you many different options within a simple interface here. So that's some of the different icons that we have for example, we start off with geometry. Now, I just mentioned that we go from left to right, and you'll see that normally not only the icons inside of each category are from left to right, but you also have, for example, these tabs up here that go from left to right, where you'll start off with your geometry. Then you have a flow tab as well, which gives you all of the tools for flow. Then you have radiation, motion, meshing, and then the solution. So normally when you set up a model, you'll tend to go through this workflow. You'll start off by cleaning your geometry, kind of like I mentioned on those slides that I showed you. You start off with your geometry. You go into your flow. You would want to set up all your boundary conditions, everything you want from there. Radiation, if you have any radiation. Motion, if you have any motion. And then from there, we go into meshing. And then that's when we would generate our mesh. After we generate our mesh, then we jump over to the solution tab. So this is where we would run the actual problem and send it to the solver. So keep that in mind, that everything is kind of laid out from left to right. So starting off with geometry, I want to just kind of show you guys, we'll go through this problem very quickly. We won't do anything too fancy on this, and we won't do any post-processing just yet. I just want to get you guys familiarized with the interface itself. So just kind of going through the different tools that we have here. This first chunk of tools that we have on the left here under the geometry tab, so make sure you're in the geometry tab. This first chunk of tools that we have here are FE geometry tools. So since we have the ability to bring in a mesh, if let's say you have some kind of mesh from another model, you can work based off of the mesh as well. So for the most part, since we brought in a geometry, we don't need to worry about any of these tools for now. The ones that we could pay attention to are these next two tools. So these are the two repair tools that we have. These will allow us to check and review our model to make sure that there's no issues with either the surfaces, making sure that there's no like disconnected surfaces, that there's no extra duplicate surfaces on top of our model or anything weird like that. It's very hard to see. And here you'll see that everything's at 0. If I jump over to the solid here, everything's at 0 there. So there's no issues with my solid. Like I don't have intersecting solids. I don't have sliver surfaces or anything like that. So these two allow you to repair any kind of error that comes in with that. From there, we have our creation tools. So here you'll see that we have the ability to create simple shapes. So I can create either squares or circles and then generate surfaces off of that. And I can also generate solid geometry as well. I can generate spheres, boxes, cylinders around my model. So like I mentioned before, this is not necessarily a CAD package. It gives you some basic tools to make adjustments to your model, but you don't have the ability to create, like for example, a model like this. It would be very difficult to create within just this surface, this software. So normally you'd bring in some geometry from some kind of CAD package, okay? So we do have the ability to create some basic geometries. Normally you'll use, like for example, the box tool for external flow applications. Like let's say you want to test the aerodynamics of a part. You can put that in a box, and then that would work as your wind tunnel. So there's different ways of going about this. So now what I want to do here is I want to show you guys how you can enter and exit different tools. So if I click on that box tool, you'll see that this little window or this little drop down pops up, right, with the little play button. And then my mouse changes, and now it's trying to create a box, which means that I'm inside of this box tool. If I click on the sphere, it'll be similar, but it'll be in order to create some kind of a sphere. If I click on the cylinder, it'll be a similar thing where I can create some kind of geometry here. If I don't want to be in this tool and I want to exit the tool, I have a couple of ways of exiting. The easiest is just pressing the escape on your keyboard. And for now, we'll just keep pressing escape. So you'll see how I was sort of in two different levels of tools. So I was within this tool here and within this here. So if I click on the cylinder, if I press escape once, it'll exit this tool, but I'm still within the solids tool up here. If I press escape one more time, then I'll be completely out of the tool here. So kind of be a little bit careful with that. Sometimes you might be still within this tool and you'll be trying to do something else and it won't let you. A lot of the time it's just because you might be within some kind of tool. The tool that I want to show you guys first is this drag and push or push and pull tool. So if I click on the top one, the little arrow here, you'll see that it'll stay blue and it'll start glowing blue. And then my icon on my mouse will change. Now what this tool lets me do is it lets me grab any kind of surface. So for example, this surface here, and it lets me drag that surface out and create a larger solid. So for example, if I wanted to extend that solid part there, I can just click that surface and grab that solid part there. I can do that for any of these surfaces here. So for example, if I grab all three of these surfaces at once, I can drag forward and I can choose a particular value that a more specific value if I wanted to, and drag that geometry outward using this tool. So this is pretty handy in some cases where let's say you want to make a slight change, you want to increase the diameter of a part, you want to decrease the length of a part. You can also push back and make it smaller as well. So right there, I've got all of them selected. So what I want to do is if I want to finalize the change that I made, so right there you'll see that it kind of reverts back to where I was. I can right click and you'll see that this little check mark, this green check mark pops up next to my mouse. If I hover over that and go to the left like that, that pretty much confirms the change that I just made. So that's one way to exit the tool and finalize the changes that I made. So keep that in mind. That's how we can do it. So that's the push tool. Another really handy tool that we have is, for example, this split tool. So you'll see that I have different methods of creating any kind of cut in my model. I can choose some kind of interactive method where I create a line and make it cut through that model. Or I can choose nodes, like different points within my model to split my geometry through. I can choose lines. Like for example, if I click on lines, you'll see this bigger bar appears on the bottom here. So if I click on lines, what this lets me do is it lets me grab, select kind of a surface that I want to cut or just kind of like make an indentation on. So I can grab this surface here. In this case, I'd be selecting a surface, and then I can choose a line. I don't have a line on this case. Let's do... I would have to create a line for this, but if I were to select a line in between the surface, it would let me split or cut through that surface there. So what I'll do, instead of cutting through this surface, something more useful than cutting through a surface is cutting through the solid, since this is a solid geometry. So if I click on the left here where it says the target, instead of having a surface as a target, I want to select solid as a target. If I select solid and I click on my part here, you'll see that I can select the whole thing at once because it's one solid part. Now, if I click on lines on the right here, this will allow me to grab any of the lines that I have on my model. So for example, this one here. And I can choose to split my geometry based off of that line. Now, this window does pop up to give me the ability to choose sort of the direction as to which way I wanted to split. So here you can see that the arrow is sort of pointing towards the Z direction. And that's because right here on this XYZ boxes, the 1 value is in the Z direction. So if I change this to 0 and I choose to do 1, let's say, actually I wanted it in the Y direction in this case. I wanted to cut down in the Y direction. So my X parameter is 0, my Y parameter is 1, and my Z is 0. So if I press enter, you'll see that now it's pointing upward. So since I wanted to point downward, what I can do is I can select -1, and now the vector will be in the negative Y direction. So here you can kind of see that it now wants to cut downward in the direction that I prefer. Now that I've selected the line and I've selected the solid and the direction, I can go up here to where it says split and click split. And it'll seem like nothing really changed right now. But if I go back to right here where it says select solids, you'll see that, oh, I guess it didn't do it. Let me try that one more time. I'll click the line here and I'll do in the -1 direction and the split. Okay, so I guess it doesn't let me use that. And that's something that will happen from time to time in some particular geometry. What you'll find is that there's different ways of cutting it. And the reason why we have different ways of cutting it is just because in certain pieces of geometry, especially if your geometry is too complicated, it won't know how to split certain pieces of geometry, or it might cut it the wrong way in some cases. So in my case right now, I guess it wasn't very well defined using that line. So instead of using lines, I could use a better method using planes. So I can, instead of selecting a line, I can specify a plane, and then it'll cut about that particular plane, which should be a little bit cleaner anyway. So one thing that you'll notice is that if one tool doesn't quite work with the operations that you're trying to do, whether it's it won't cut it or it'll cut it the wrong way, I would sometimes recommend trying the different methods that we have on here. So in this case, I'll use the plane tool. So we'll try the same thing with the plane tool, and I'll change this from target to solids. Or the target, I'll change it over to solids here. So once that's changed to solids, I'll select this solid geometry here. And you'll see that now if I click the tool option here, the tool will be represented with this little like chainsaw, which will kind of cut to define what the direction would be. So if I were to choose the point here on this line, it'll cut it in that direction there. So it'll be sort of cutting it lengthwise in this case. If I select it on this edge here, or anywhere along this plane here, it'll cut it in this direction, like kind of across the surface here. So ideally, let's say I want to make a cut here. I can just select a point in the middle here. It'll snap to points of interest a lot of the time. So that's very handy to use. Technically, I can choose anywhere in this surface here. But ideally, you would want to snap to one of these midpoints on your model. So in this case, I'll stick to this line, and I'll select this midpoint here. And you'll see that it'll give you a preview as to where the cut will be. So right here, it's sort of telling me that it will cut across the pipe here. So it's showing me sort of the cut surface there. If I click on this back arrow here, this triangle with a little line on it, this will deselect what I just chose. So it'll clear my selection if I want to try something different. So if I click on that and I see that the cut's not what I wanted, I can clear my selection using that button there. So what I want to do now is I want to grab it again, and I want to show you guys how it can demonstrate in the different directions. So if I choose it on this direction, you'll see that now that red surface goes across my pipe here. So that's demonstrating which direction you want it to cut. So in this case, I want to deselect it again, and I want to cut across this here. So I'll select my solid using the target here, and then I'll select the cut here. Now, once I've done this, I can click split, and now you'll see that an extra line will appear where I cut that geometry. So what I want to do now is I want to exit this tool. If I press escape twice, you'll see that I'm out of the tool, and this little bar on the left here will pop up. And what this bar on the left here does, this is our selection tool. So this lets you choose what exactly you're trying to select. So let's say I want to grab only that section of the solid that I just cut off of this part, right? So I want to select these two separately. Currently, the selector is set to parts. So if I click on this, it'll just grab the entire thing because it's all set to part 1. If I change this, if I click on the little arrow here, you'll see that I have a bunch of different options. I'll have parts, solids, surfaces. If I select solids, I can grab different parts of the solid here. So you can see now these are two separate solids. Another way to tell that that cut that I just made worked is looking at the list of parts that I have on the left here. I have two solid bodies now, and they'll have a similar name because it's derived from the same solid. So I can grab these two here. I can select them separately, and I can change to either surfaces if I want to just select a certain surface on my model. I can change this to solids like I just had. I can change it to lines. In this case, I'll select those two solids. So now that's our cut tool. So that's our split tool that we have here. That's a very handy tool that's used pretty often, I should say. Another thing, and I'll explain what are some of the good uses of splitting something like this. Another thing that I want to talk about is this stitch tool. So this stitch tool lets you stitch surfaces together, but the one right next to that is this suppress edges tool. So what that suppress edges tool will do is if we go into our model here, we can grab, for example, I'll press escape here just to kind of clear my selection. But if I click the suppress tool on the left here, you'll see that I have a bunch of lines in this model here. So what I can do is I can select, I can select two different surfaces. And what I'll do is I can suppress all of the surfaces that are between those two surfaces that I just selected. So for example, if I go down here and I suppress all of those surfaces there, you'll see that if I press escape, they become dotted lines. Now what this means is that when they become a dotted line, once I start generating the mesh for my model, it will ignore that line. So it'll start generating a mesh as if that line is not there. And the reason why that's important is because sometimes when you start looking at your model, if you go into regions like, for example, down here, you'll have some surfaces that are very, very, very small, and that will cause some problems with meshing because they're just so tiny and the mesh is trying to fit elements in that region. So sometimes it's important to remove some edges. Now, you'll see that as I hover over the surface, it'll try to select the entire surface there. But if I hover over the line, the actual line itself, right here, you'll see the icon changes and then it lets me select that line. If I click on just the line using this tool, you'll see that it'll suppress that one that one line right in the middle there. And this is handy, for example, in this case, where that line really wasn't doing much. It's not really helpful, and it might just cause issues with meshing. So there's different applications to this. If I go around my model, I don't think I have any other little lines like that, but that is a very useful thing to use when you're having problems meshing, or when you have such a complicated geometry that you have a lot of these edges on your model. So that's how that suppress tool works. It's also a very handy tool to use. And let's see, before I go into any other tools, do you guys have any questions regarding the tools that I just covered? You guys can use the chat box for any questions that you guys might have, any comments you might want to make as well. Okay, so this is all pretty straightforward so far. Uh, the next thing that I want to discuss here is the Boolean tool. So in some cases, you might bring in different solids or different parts, and you might want to combine them together or make sure that they're attached to each other so that when you generate a mesh, the meshes at least connect to each other. So in some cases, you might bring two parts that are attached to each other. If I were to just mesh these two parts, so for example, as I mentioned before, I have two different solids here, right? I have this solid on the right and I have this solid on the left here. If I were to try to generate a mesh, sometimes if I were to just import this like with two different parts in it, it might not know that those two are connected and the meshes might not line up. So one thing that's good to use or to do sometimes is to make sure that those two are attached to each other or connected. And one way that we can do that is by using this Boolean tool. If I click on this Boolean tool, we have the ability to do different things. We can either combine different solids, we can subtract one solid from another solid, or we can grab just the intersecting section between two solids as well. So that's what these three tools are useful for. So combined is mostly useful for that situation I just mentioned where you have two different solids that you want to make sure they're attached to each other. Subtract is useful for, let's say, you make a wind tunnel and you want to subtract the solid part from that wind tunnel so that you only have the volume of air around your part. Like you don't really care about the solid part inside of the of your model. You only care about the actual fluid itself, right? That's the big thing. So sometimes you'll bring in your model. Let's say this is going to be an external flow application. You'll create a box around it and you'll subtract your model from that box. That's when you'll use that subtract tool. So those are some of the uses for these tools. Right now, what I want to do is I want to click on the combine tool and I want to grab these two solids together here. So in this case, since they were created from the same solid, it won't really pick it up. But if I grab these two solids like that, let me show you again. If I grab this solid and then I select this solid here, it'll turn red, and you'll see that as it's red, if I hover over it, a little check mark comes up. And what this will do is it's sort of a way to confirm that I want to combine these two together. So now if I want to combine them and just have one solid part, I can just click combine all and it'll make it one part. Now let's say these are two separate parts and I want them to be connected, but I don't want them to be one solid part. I want them to be two separate parts, but I want them to be connected. In that case, you can choose this keep common interface. And what that'll do is it'll grab these two, it'll connect them, it'll make sure that they're attached to each other, but it won't unite them. It won't make it one solid. So this is a very handy tool to, or something very important to keep in mind here. So what I'll do is there's a couple of things I can do. I can either click combine all, or I can go over and on the red region, I can just click on it once, and you'll see that it confirms the operation that I wanted to do. So if I grab these two and I click on the check mark, then it'll combine them together. In this case, since they're both, since I kept the common interface, they're still separate parts. Those two, there's two separate parts on there, but they're connected now. If I were to uncheck that box, and then I did the same operation, so I selected both of them, and then I click on it, you'll see that now it's one solid part. So whenever I click on it, it's one solid part on there. So that's the difference of using that keep common interface. Before, it connected them, but it kept two separate parts. So that's a very important thing to keep in mind when using this Boolean operation tool. Okay, so now, for those of you guys that are used to HYPERWORKS Classic, I know a lot of you guys are probably used to working based off of components and reorganizing components and moving components around. For that type of workflow, now the workflow has changed quite a bit to make it a little bit more streamlined and a little more intuitive in general. So there's a lot of changes that have happened. We don't quite work based off of components anymore. But we do work off what we call groups, which we can I guess we can kind of relate one to another. But the idea here is if we use the groups tool, The groups tool lets you create, as the name entails, groups, right? So you'll be able to create different either groups of parts, groups of surfaces, or groups of lines, and so on and so forth. In this case, for example, let's say I know that I'm going to set the same inlet velocity for these three pipes right here. Let's say those three are going to have the same boundary condition, whether it's an inlet velocity or whether they're all outlets. I think in this case, the inlet is on this larger side on the left here. So this is where that inlet would be. And the outlet would be these 3 points right here. So since I know that those three are going to be behaving the same, I can group those three things together. So what I'll do is I'll change this selector to surfaces. Right after we click groups, I change this to surfaces. And then what I want to do is click on each one of these surfaces here. Now, once I've selected all the surfaces that I want to group up, I'll click this check mark, and that'll create a group. And it's not necessarily visible anywhere in here, but if I hover over the groups icon, you'll see that there's this little box underneath that pops up. If I click on that, that's where you'll see the list of the groups that you've created. Now, once you create this group, the good thing about it is that once I go into anything else, once I start defining boundary conditions or meshing parameters or anything else, I can select by group as well. So now that I've defined that as a group, I can go on and use other tools. And whenever I need to select a certain group of surfaces, then I will just refer to that group every once in a while whenever I need to use that. So that's really handy in the sense that, let's say you have some very complex model that has a lot of inlets or a lot of outlets or a lot of geometry that's very similar that you need to control at once. Groups would be the best way to kind of keep everything together. So that's how groups work, and I'll show you right now how to refer back to them. But let's say we're done creating or manipulating our geometry, right? So there's a few other tools that we can use, but I'll be covering those later on. For example, the defeature tool I'll cover later on, the plug tool I'll be covering later on. But for now, let's just kind of keep going. I don't want to overwhelm you with all of the options. So now the next thing that we would do is, since we're done with geometry, keep in mind we go from left to right. So we work our way from left to right. So now we're done with geometry. So the next thing we want to do is flow, right? So this would be where we set up our boundary conditions for our model. So now we're going to set up some boundary conditions for this model here. What we want to do is we want to start off from left to right, all right? We always work our way from left to right. We'll start off by clicking on this physics button. So this physics button will let you select all of the solver parameters. So all of the information that the solver needs as far as, you know, how many iterations it's going to use, whether it's going to have heat transfer or not, all of these basic parameters. And I'll cover all of that in detail on the future models. Right now, we're just getting used to the interface. So don't worry too much about the parameters just yet. I'll break those down on the following models that we'll be working on. So for now, this is where we'll be able to define things like steady state or transient. We'll be able to define things like turbulence models, or if it's a laminar flow. We'll be able to turn on the heat equation if we want to. If we're using multiple types of fluids, like let's say there's a tank with air and water, then we'll be able to control that in here. We have solver controls. This I'll break down once we get to that point. But for now, we don't really need to make much change to or any changes to this. We'll just leave it as it is. But yeah, we start off from the left and we go to the right. The next thing is the material library. So in this library, this is where we would be able to create any kind of materials that you might need for your model. So if you're using some kind of special refrigerant or some kind of oil or some kind of, I don't know, a different type of non-Newtonian fluid or something like that, there's a lot of different parameters that you can define within the material library, which then you can reference later on. So this is where you would just make your library of materials. So we'll close that for now. The next icon here is the materials icon. So this is where we actually assign the materials that we want to define. So In here, we'd be able to click on whatever solid we want to define. Right now, by default, everything's set to air. But here, I can click on this drop-down and select what type of material it is, whether it's air, water, and then you'll see some of the aluminum and stainless steel, it would automatically define it as a solid geometry. Or we could also define it as a void if it's some kind of geometry that you just don't want to consider, or a part that isn't really important. You only care about the external surface of it. You can set that as a void as well. In this case, it's just going to be air, and we're just going to click the check mark. So the next thing that we want to do is we have a bunch of other options that I'll go into later on. But the next thing that we want to do is we want to define our inlet condition. So our inlet condition, you'll see we have a couple of different options. We have what's called a profiled, and we have a constant inlet condition. For now, we'll just be using this profiled one. I'll explain what the differences are later on. But for now, this is going to be defining what our inlet condition is. So we'll click on this profiled inlet condition, and I click on this larger surface on the inlet here. Now, once I click on it, you'll see that it'll list an inlet here. Currently it has 0 surfaces attached to it because I haven't confirmed it yet. And there's 28 surfaces in my model that are defined as wall by default. So when you first start defining everything by default goes to wall. And then we start defining what is not a wall. So what we want to do is we define this inlet, and we define what the average velocity will be for this. So if I press 2 here, I'll specify a value of 2. And keep in mind that this is all going to be in SI units. Everything is metric. Everything is SI. So you'll be doing meters per second in this case. Temperature is Kelvin, and dimensions are in meters as well. So just kind of keep that in mind for now. I know it doesn't show units. I believe the developers mentioned that that's something that they'll plan to add soon to this. But for now, this is just specified as just a there's no units to the value here. But keep in mind that everything is metric. Everything is standard SI units on this. So we'll set this to 2, and we'll click the check mark here. So if I click the check mark, you'll see that up here where it says profiled, now I have a number 1 on top of that. So you'll see that where the icon is, right above it, there'll be a number 1. That means that there's one surface that's defined, or there's one boundary condition created as a profiled already. The next thing that I want to do is I want to define the outlet for this. So I go over here to outlet, and I click on this outlet boundary condition. So what I want to do here is I want to select all of these outlets here. Now, if you guys recall, we created that group so that we can just select them all together. So whenever you see this little plus sign on a tool, so any of these tools, like whether it's this one, all of these that have a little plus sign on it, whenever you see this plus sign, that means that you'll be able to choose an advanced selection. So this is kind of bringing up the advanced selection option. So I can choose a category to select different things at once. So for example, right now, everything's a list of boundaries. So I can select everything by boundaries if I wanted to. But if I click on that, there's a list of different ways that you can select different things in your model, which is handy when you have a very complex model. So for now, you can see that we have here that's set this option that says by group. So if I click on groups, it'll list all of the different groups that I created down here. So right here, you can see that I have this surface group. So I can click on that, and it'll automatically select all of the 3 surfaces that are in that group here. So here you can see that I can now set the parameter for all 3 of those, which is a very handy way to select different things. And we're kind of encouraging everyone to just use these groups often. It makes everything very easy to keep under control, especially when you have a very, very complex model. So for now, we don't need to make any changes to this. So all I need to do is click the check mark. But now you see that we also have this little like black triangle. It's kind of like a play button. If I were to select that instead of the check mark, then what that'll do is it'll create what I just selected, but then it'll stay open for me to create more of that if I wanted to. Okay, so that's the difference between the check mark and the little play button here. If you press that little triangle, you'll be able to create more of the same tool that you're using. So if you have different inlets, you can, with different boundary conditions, you'll select the surface and then you click the little play button here, and it'll jump to the next thing so that you can create another one right after. When you click the check mark, that finalizes everything. It closes the tool, and then you're done. So that's the main difference between these two here. So I'll just click the check mark, and that means that my model is pretty much done here. So since the rest of my walls or my surfaces are all wall, pretty much that's all I need to define here. So that's how we would define, these are some just of the basics of how we would define the boundary conditions. We'll get much more into this once we go through the model. Like I said, my goal for today is to get you guys familiarized with the interface, okay? So the next thing that we want to do is we're not going to use radiation. So again, we always go from left to right. Keep that in mind, left to right. So we go to radiation, we don't have any radiation. We click on motion, we don't have any motion on this model. So the next thing is the mesh. And this left to right method is really handy because it lets you keep track of what's the next thing to do, what you're missing, or where you're at through your process, right? So it's really nice to kind of keep that in mind, that you can go from left to right. In this case, we're just going to generate a very coarse mesh, nothing fancy, nothing special to this. But there's two different ways of creating a mesh on this. So we have these mesh controls that sort of let you grab your model and generate a mesh around your model. You just give it parameters. You tell it, I want this size of a mesh around here. And then you mesh everything at once you've defined everything. Or there's the HyperMesh classic way of doing things, which is more the interactive way as well, where you can grab, for example, if I click on local, I can grab my surfaces here. So I can just click and drag and select all of my surfaces. And this will give me a sort of like an estimated value, right? So it'll find what it needs, or sort of like a rough value that you could use for this. If I click on the little three lines here on any tool, you'll get extra options. So if you see these three little lines at the beginning of the tool, this is a little hard to see, but these three little lines here will let you give extra options and parameters for that tool. If I click on this here, you'll see that it's currently using an average size of 0.02, and it allows me to manipulate that if I wanted to. So if I click mesh here, you'll see that it'll create a fairly coarse mesh, but it'll create a mesh around my model. And this is an interactive way of doing things. Now, let's say I'm not happy with this mesh. I want to get rid of it. Over here where it says batch, you'll see that this X appears when you hover over it. So if I move my mouse over to batch on the left here, a little X appears, which allows me to delete whatever mesh I have created already. So I'll click on that red X, and that'll remove the mesh that I just created on here. The method that we're going to be using more often, that's kind of just to create, like, let's say there's a certain surface that's problematic. That's normally sometimes when you'll go into it and do like a little bit of surgery and try to clean that mesh locally using the interactive features. But for the most part, most of the time, you'll be using these mesh control features. So again, this works the same way. We go from left to right. So we'll start off by creating a surface mesh. I'll click on this surface button here. And right now, I just need to select all of the surfaces that I have right here. It'll ask me what element size I want. If you remember from that previous mesh, it created something like a 0.02 element size. So we'll use a 0.02 in this case. And we'll just, once we've defined that, we'll click the check mark. And you'll see that now I have one mesh control for all of my surfaces. If I click on that button again, you'll see the list of surfaces here. And you'll see that I've selected pretty much everything on here. The next thing that I want to do is I'll go over to edges. I don't need to create any edge meshes, so I'll skip that. Gaps, there's no gaps in my model, so I'll skip that as well. Angle, I don't need to worry about that, so I'll skip that also. Boundary layer meshes, These are very important, and I'll really break these down. I believe I'll probably cover that in tomorrow's class. For now, I'm not going to put a boundary layer mesh on this, just because I really want to make sure I talk about it with you guys and break it down. There's a lot of options that go into this. So for now, we just won't worry about this now. So then the next thing that I want to do is create a volume mesh. So this is the parameters of what mesh size I want to choose for all the elements inside of my model. So if I click on this, I can select a solid part, and I can choose a parameter that I want for this. I'm going to choose a similar size to my surface mesh, so I'll do 0.02. And you'll see that these little dots will be coming out to kind of give you an idea as to how coarse the mesh is. It just gives you a rough idea as to how small it is. So if I do 0.01, you'll see that I have more of those little nodes that appear through my model. And that's just to kind of give you an idea of the scale of the mesh that you're doing, so that if you go in here and you do 0.001 and you don't see the element or the nodes, you'll know that your mesh is too fine and you don't want to do that, right? So, or on the other side, let's say I choose a size of 1, you'll see that there's no dots on there at all, and that's because it's one massive element here. So you don't want that either. So we'll do 0.02. We'll keep it at 0.02. And then we'll just click the check mark here, and we're pretty much ready to generate a mesh. So now that I've done this, I've created I have my parameters for the surface mesh. I have my parameters for the volume mesh as well. So now that I've defined all of my mesh controls, what I do next is I use this batch mesher. And what this will do is it'll look at all these parameters, and it'll generate the mesh for me all at once. So if I click the little play button here, sometimes you'll see this if you want to create a simulation model. You just click yes on that, and you'll see that it will jump back to a geometry. And the reason why it's doing that is because before it generates the mesh, it'll do these validation checks here. So it'll validate, it'll check your surfaces, it'll check your solids, it'll make sure that there's no errors on your geometry, so that when you create the mesh, you don't get any problematic elements. Or it'll try to avoid them as much as it can. Because sometimes, especially when you have a very large or very complicated model, you'll spend a lot of time generating a mesh, and then you'll have problematic elements, or it'll just error out and not give you any mesh at all. So it's nice that it now it does these checks for you before it generates the mesh. So if it jumps back, you'll see that it will jump to geometry. If you have this little blue check mark on the top, it means that everything is 0 and 0 here, and it's ready to go. Sometimes it'll turn yellow if there's some problems that you might need to fix, but for now it's blue, which means that we're ready to go. So if I go back to mesh, the meshing tab, and I click on that play button again, so I'll go over to the batch mesher and click the play button, then what I can do is I can either select whether I want to just generate the surface mesh alone, or if I want to generate the surface and the volume mesh. So what we want to do is we want to generate both the surface and the volume mesh, unless you just want to check the surface mesh first. In this case, we'll keep it as a surface mesh and volume mesh. And you'll see that I have another parameter here for average size. And the difference between this and the parameters that I set is that this is sort of like a global parameter. So these mesh controls up here are sort of your local parameters. So like, let's say you have one surface that you want to have that's very fine, and the rest is going to be just coarser. You use these local parameters up here, and then you have this global parameter over here. So anything that doesn't have a rule, anything that doesn't have one of these parameters, like for example, if I didn't define a volume mesh, what would happen is it'll just default to whatever the average size is here. So these are sort of the global parameters. That's the parameters it'll use for everything that doesn't have a rule. Since I created a rule for all my surfaces and I created a rule for my volume mesh, then this doesn't really matter. Like, it won't make a difference what I have here. Now, if there was some kind of surface or volume that I didn't select or I didn't define, then it'll matter. Then it'll look at this and define it by this. Okay, so now I'll click mesh here, and you'll see that this little window will pop up, and this is the meshing process. So this is where it'll start generating the mesh for you. So this will take a little while, not too long, depending on how find your meshes. But seeing that sometimes this could take very long depending on how fine your mesh is, that's why it's important to have those geometry checks before you generate the mesh. Okay, so once this is done, if I close this window, it'll show the mesh that it created for me here, right? And if I want to check my volume mesh inside of this, then I can use that section cut that I showed you guys at the beginning that I was hiding the whole time. So if I bring that little checkbox up again, you'll see that it'll show me my mesh inside of my geometry here. So I generated a nice volume mesh and a surface mesh. This is not ideal. This is just to kind of get you guys an idea as to what's going on, because like I said, I just want you guys to get familiarized with the model, with the interface here. Okay, so now that the mesh is generated, the next step, looking at the top here, is the solution. And in here we have a bunch of options that let us kind of probe or set little points of interest in our model. Like, let's say if there's a very important thing for us that we want to pay attention to, like let's say you want to know what the temperature is inside of this part here on this surface. Let's say the surface is important. Then we can define that as a monitor. So you have these monitors here where you can choose a point, choose a surface, or choose a volume. And what these monitors will do is that it'll write out the solution for that exact surface. So if there's like a surface of interest or anything that's important to you, you can define it using these monitors. And then when you run the solution, you'll have sort of like a separate section for that surface so that you can plot that separately or look at anything important separately on that. So I'll go into that later on. For now, we just want to run this. So the way that we would run it, we will go over to this run icon here. We'll click on that and you'll see this little window pop up. Okay. So now one very important thing for this, especially if you guys just installed the software, this AccuRun path is normally not defined by default. You might have something blank here. So what you want to do is you want to specify where this accurun.bat file is. You guys can take a screenshot of this here so that you can, mine is installed in the default directory. So if you have it installed in the default directory, this is the path for that. So if you guys want to input that value there, what I can do is I'll copy and paste it on the chat as well for you guys. If you installed it somewhere else differently, this might be a little bit different. But after this alter folder, this 2020, that's where you'll locate the AccuRun path. Okay, so this is important to define before you start running any simulation. Once you define this once, that's it. You don't have to define it again. So just, if you have it blank right now, just make sure you have that added on there. Okay, so now once we click run, you'll have the problem name. You have this problem name here. You'll have the problem directory. So this is where everything's going to be saved. And in this case, we're just going to leave it as the name of whatever you save your file as. That's what it'll default to here, but you can specify it as something else. Like, for example, if you want to do multiple different runs, you can change the name of the run here. And this will get everything ready for you to do the solving stage. So just to reiterate what I mentioned about pre-processing, solvers, and post-processors, the pre-processing stage is everything that we just did. Everything in this piece of software, HYPERWORKS CFD, that's what we call a pre-processor. So once I get this ready and click run, what this will do is it'll write out a bunch of files and it will send them over to AccuSolve. So AccuSolve is the solver, right? So it'll just send it over there. You won't really see anything here. It'll do all of this in the background, but it'll grab this model that we created. It'll send it to the solver, and then the solver will give you an answer. Okay, so that's how this works. So in this case, we're going to leave it as manifold. I'm just going to save it to the directory where I have everything on here. And then in this case, we don't need to change anything else. I'll break all of this down later on. For now, we'll just click run. And when I click run, you'll see that right now it takes a little while because it's exporting the model to the solver. And now you'll see that right here it says AccuSolve. That's because it sent this model over to AccuSolve. And that's how you would submit a run to AccuSolve and get your model solved. Okay, so I'm going to cover how to look at your results later on, and I'll cover how to monitor and plot all of this stuff later on. For now, I think that's really all the material that I wanted to cover. So what I'll do for now is I'll take a couple of minutes while this is solving, while this is done, running. I want to just take a couple of minutes to take any questions on anything that you guys might have. Again, like I mentioned, there's going to be a lot of stuff. I'm sure a lot of intricate questions might come up. Right now, I know there's a lot of things that aren't very clear. There's a lot of options that I haven't covered yet, but I will be covering those. I just wanted to kind of introduce you guys to the interface here. So Aldo, your question. So this question is, if you have several parts that are connected but not joined, can you create individual volume meshes and then somehow stitch it all together in the end? So you could stitch solids together after you've meshed them, but I don't recommend doing that. So the reason why you want to make sure that your geometry is all stitched together and connected first before generating a mesh is because if you have a mesh already on your model, like if I were to make any kind of Boolean operation on this model that I have now, like it is now, it's going to start trying to remesh every single change that you make. So every change that you make, it's going to do this step here of remeshing the model for you, and it's going to take a long time to do that. If, let's say, you generated your model, you made a mistake, and you want to stitch it together, you can do that. That's perfectly fine. And for the most part, you can, if you have the geometry in the model, you can use the geometry tools. So you can use these Boolean operations. Is probably the best way to do it. If they're volumes, using the Boolean with the, you see right here, it's even warning me that if I do any changes, it'll remesh. It takes a while to make changes to this. So the Boolean operations would probably be the best way, but you do have these mesh fix operations. So you have these options to edit and combine and edit the mesh itself. These tools are normally meant for you when you bring in a model that has a mesh already, or it's just a mesh, you don't bring in any geometry. That's when you usually use these, but you can still use them on this model as well. So depending on your setup, those are the tools that I would look at in order to try to connect things that might be separate without, breaking the whole thing.